All right, so yesterday we talked about this situation here, okay, and how these two people do the same amount of work, okay? And they do the same amount of work because the definition of work is that work is a change in energy. And they change the energy of these two masses by the same amount, regardless of how they get them to the top of the ramp. Okay, everyone follow me on that one. All right. Now in this situation here, okay, we were talking about this as well, and we said that by pulling back on the box, okay, we lift the ball, and we give it what kind of energy? Okay, mechanical, specifically what kind? Potential energy, gravitational potential energy. And we can calculate how much of that we give it, okay, by going m times g times h. All right, everyone with me on that one? All right, so when we release this, the whole system will have that much mechanical energy because no more work is going to be done. We did work in pulling the ball up, and that's it. Now the system has that much energy in it. Okay, the system sort of decides where that energy goes. Okay, everyone follow me there. Okay, so if I do 49.05 joules worth of work, okay, in lifting that up, how much work can the system do? Exactly the same amount, 49.05 joules. Okay, there's no more sources of energy to do more work on it. That's all the work that that system can do because that's all the energy it had. Okay, all right. Now, for potential energy, okay, we said that the formula for potential energy is m times g times h. Okay, mass affects potential energy, gravity affects it, and the height above the ground. Obviously, the higher above the ground you are, the more potential energy you are going to have. Okay, because the faster you'd be going when you reached the ground. Okay, everyone follow me there. Right. Okay, so other little things to remember. Okay, m has to be in kilograms. Okay, anytime in physics that we deal with mass, it's going to be in kilograms. Okay, energy obviously is in joules, so is work. Okay, g is acceleration due to gravity. That number is pretty much fixed for all the questions that we're going to do. It's 9.81. Okay, and h, like we said, is the height above the ground, and that also always has to be in meters. Okay, so if we have a simple example here, 3 kilogram box lifted by an upward force 1.5 meters above the ground. Okay, if we wanted to find the potential energy of the box in that position, we'd simply go mass times gravity times height. Okay, and that's what we do here. 3 kilograms times 9.81 times 1.5 meters gives us 44.1 joules. So now that box has 44.1 joules of gravitational potential energy. How much work was done? 44.1 joules. I think you would agree that when it was on the ground, it had no potential energy. Yes? When it's in its new position, it has 44.1. Its energy changed by 44.1 joules. That means that's how much work had to be done to lift it there. All right? That's that thing we got to remember. Okay? Work is a change in energy. If I change energy by a certain amount, that's how much work I did. Always. All right? Okay. Hey, another example, if we needed to manipulate this formula, is this going to be a pretty easy formula to manipulate? Everything's being multiplied, right? So if you want to move anything, you just divide all the other stuff away. Okay, if I want to solve for h, I divide both sides by mg. Okay, goes over to the other side. All right, so we have a 55 kilogram diver, okay, and they have 5,400 joules of potential energy standing on the platform. All right, so we want to solve for h, so we divide both sides by mg, as you see here. Okay, and we get 5.4 times 10 to the 3 joules divided by 55 kilograms times 9.81. Now, a little trick here, because sometimes I see people make this mistake. The way this is written, I would not get 10 meters. Because your calculator, when you do this, wants to do order of operations. And if you let it, it will screw this up. You have to do the whole bottom, okay, and then divide the top by that whole number. Otherwise, it goes 5,400 divided by 55 and then multiplies by 9.81. Okay, so just always kind of be mindful of that. Okay. All right. So it ends up being a 10-meter diving platform. Everybody okay with that? Questions there? Pretty easy, right? All right, now for kinetic energy, okay, I'm going to show you a couple of examples of using kinetic energy to do work. That is, people who break stuff with their hands. Okay, wood, sidewalk blocks, bricks. Okay, pretty cool stuff actually. I just find that the people that can do that, it's not because they're incredibly strong. In fact, I'm going to show you some. This one is this really skinny old guy. Okay, and his is actually kind of painful to watch because it takes him a few swings before he breaks it, and it's just, you're just like, oh, come on, please. Okay? But you don't have to be incredibly strong to do this. You just have to have the right technique and the proper mental focus, okay, in order to pull this off, as well as the right setup. If the setup isn't right, it doesn't matter how strong or how good a technique you have, you're not going to break nothing. Okay, so potential energy, if the object starts to fall, will be converted, not lost. It'll be converted into kinetic energy, because we all know that when something falls, it starts with A, accelerates. Yeah, okay, it accelerates downwards when it's falling. That means, as it's falling, its height is decreasing, but its speed is increasing. All right, so when an object is dropped off of a building, let's say, okay, it has a certain amount of potential energy. When it reaches the ground, it has no potential energy, but it still has mechanical energy because it's moving really, really fast. All right, all of its potential gets turned into kinetic. So if it had 150 joules of potential at the top of the building, how much kinetic will it have at the bottom? 150 joules. Okay, and why are they the same? Because to carry it to the top of the building, you probably did 150 joules worth of work. Okay, you changed its energy by 150 joules to take it up there. Now, okay, it has that much potential. When it reaches the ground, it has that much kinetic. And if there was something underneath it, it could do 150 joules worth of work on that thing. All right, everyone follow me here? That work energy theorem. They can be converted back and forth. Energy can do work. Work is a change in energy. Okay, those two things are just kind of always linked together. All right, I'll show you these videos here. I gotta pause that. I'm recording it. I'll get in trouble. No, really. You laugh. I will. I got a copyright strike against me once on YouTube for that. All right. So we use kinetic energy to do work because potential energy can't really do any work unless it's converted into movement. Okay. Just having something sitting on top of a building doesn't do us much good. Right? It doesn't do us any good until it's actually moving. So, I mean, if you took a hammer and went, all right, and put the hammer here, it's not going to pound a nail. Right? It's not going to pound a nail sitting there. It has to be swung. Right? Once it has kinetic energy, then that kinetic energy does the work. All right? Same thing with hot steam turning turbines. You get steam moving, and it can turn the blades of a turbine, and that can generate electricity. Okay? Moving molecules in a sound wave can make your eardrums vibrate. Okay, that's how sound is transmitted, right? You got the little flap of skin, okay, that is your eardrum, and it is a very thin flap of skin. Okay, vibrates back and forth with sound vibrations as they hit it. Okay, if you hit it too hard with sound, it can rupture. Okay, or if it's repeatedly exposed to really loud sounds, the bones it's connected to in the middle ear begin to deteriorate. Okay, have you ever had that ringing in your ears? Yeah. Okay, that's actually the result of you having damaged the bones behind your eardrum. Okay, just like any other joint, there's several little joints between those bones, just like your knee, your shoulder, your elbow, your ankle. If you hurt it, it swells. Okay, well the joints between those little bones swell up, and then they move too much, too freely, just like any other joint when it's swollen, and they send to your brain constantly that they hear a sound because they're moving. Okay, and when they're not supposed to be, like when you turn your head, they'll move a little bit, and they'll send this signal to your brain that says, we hear this ringing, okay, even though that sound doesn't exist. All right, keep that in mind when you're listening to your headphones way too loud. Okay. All right, now kinetic energy. Okay, Kinetic energy is obviously due to movement. Okay, when a solid object moves, all the molecules move in unison. Doesn't necessarily need to be, well, sorry, when a solid object moves, all of them move in unison. If I have a fluid, okay, all of the particles may not be moving in unison. For example, the air around us is a fluid, but the particles that make it up are all moving. They're just moving randomly. That's why we don't feel them. Can you imagine how annoying it would be? Okay, if they were all moving and we could actually feel them all? It'd be like you were constantly getting hit by bugs all the time. Right? You'd go insane. Right? Now, sometimes can we feel the particles in a fluid moving? Yeah, like wind. Right? That means now we've got a lot of the air particles moving in unison. Now they essentially comprise a big mass of air that's moving towards you, and it can do work. Okay? If it's a really windy day, it can push you around. Okay. All right. So looking at this example here with the roller coaster, okay, we have to remember one big thing, and we talked about it first day of this unit, that potential energy plus kinetic energy equals mechanical energy. All right? The mechanical energy of an object isn't going to change unless we do work and change one of these kinds of energy. Okay? But if we're looking at, let's say, a roller coaster that's at its highest point, okay, it has some kinetic because it'll be rolling slowly. It has lots of potential because it's way above the ground. Okay? I add those numbers together, I get mechanical energy. As the roller coaster goes down the hill, potential energy is going to drop. Kinetic energy is going to rise. Mechanical energy is going to stay the same. Okay? We call that the law of conservation of energy. Unless you do work on a system or an object, its mechanical energy is not going to change. Okay? Or unless it does work on something else. Okay? Now you've probably noticed with roller coasters, maybe you haven't, but I'll tell you now, the first hill is always the highest one. There is no other hill on the roller coaster that is higher than the first. Why is that? What? Right. You need the energy to finish the rest of the roller coaster. If you make any hill as high as the first, it won't make it up that hill. Right? It loses energy to what we call non-conservative forces, friction mostly. All right? I mean, when a roller coaster is running, can you hear it? And I don't just mean the people screaming their guts out on it. Okay? It makes noise, right? Like it's grinding and rolling and things like that. Well, sound means that it's losing some energy. Okay? It's doing work against friction. Okay? It's losing energy there. Track and wheels probably get hotter as it rolls, okay, because there's friction there. So, yeah, no other hill can be as high as the first because it loses too much energy as it rolls, and it wouldn't get back up to the top of those hills. All right? Everyone follow there. Okay. So, kinetic energy. Formula for kinetic energy is this. EK equals 1/2 mv squared. All right? So, two things affect the kinetic energy of an object. Mass and speed. Now, looking at that formula, which one has a bigger effect on kinetic energy? Mass or speed? Why? Because speed is squared. Okay? If I double the mass, I'm going to double the kinetic energy. It's a linear relationship. But if I double V, okay, let's say in the first situation V was 1. 1 squared is 1. Okay? But in the next situation, I double it to 2. 2 squared is 4. I've just increased the kinetic energy by a factor of 4. Okay? I doubled the speed, but I increased the kinetic energy by a factor of 4. All right? That's a big deal. Okay? Speed is exponentially related to kinetic energy. Speed is exponentially related to kinetic energy. How many of you have your learner's license? Okay. How fast are you allowed to go in a school zone? Playground zone? 30. Yeah. Okay. Why? So you can slow down faster. Speed is exponentially related to the amount of energy you have. And how much energy you have is related to how long it will take you to stop. Okay? I'm going to show you a little thing here. This is not something they include on the driver's exam, but should. Okay? What do you think the odds are that my markers are working? Yeah, That's what I thought. Okay. All right, here's what we have to realize, guys. Work, obviously we've said this a bunch of times, is a change in energy. Let's say I'm traveling through a school zone at 30 kilometers an hour. Okay, 30 kilometers an hour is 8.6 meters per second. Let's double check. 8.3. Okay, so speed limit in a playground zone is 8.3 meters per second. All right, what's the formula for work? Anybody remember? Force times distance. Okay, what kind of energy would we be changing if we were trying to stop? Potential or kinetic? Kinetic. Okay, mechanical as well, but we'll just say specifically we're looking at kinetic. Okay, so that's going to mean final minus initial, right? That's what delta means. So 1/2 mvf squared minus 1/2 mvi squared. Everyone okay so far? All right. What's my final velocity going to be if I'm trying to stop? 0. Okay, so what's 1/2 mvf squared then? 0, because v is 0. Okay, so I'm just going to take that right out of here. Okay, don't need that. So force times distance equals my initial kinetic energy. That makes sense. However much energy I have when I'm rolling along at 30 kilometers an hour, okay, is how much work my brakes have to do in order for me to stop. Okay, they've got to turn that kinetic energy into heat and sound, and they got to do it quick. Right? That's what your brakes do. Okay? If you've ever watched racing at night, you can actually see when they apply their brakes because the rotors glow red. Okay, they get that hot as they apply the brakes. Okay, so your brakes turn your kinetic energy into heat and sound, and they do it really, really rapidly. All right, so let's say we're going to fill in some numbers here. I'm going to say that your brakes can exert 10,000 newtons of force. Okay, so our force is going to be 10,000 newtons. And let's say the mass of our car is 1,500 kilograms. Okay, so those are the numbers we've got. I want to figure out how far it will take me to stop. So how do I get d by itself? Philip? Right, divide both sides by f. All right, so f is gone. This is what I've got. 1/2 mvi squared over f will give me my stopping distance. Okay, so if we fill those numbers in, okay, so d equals 1/2 times 1,500, okay, times 8.3 squared over 10,000. All right, so 0.5 times 1,500 times 8.3 squared, okay, divided by 10,000. All right, so in an average size passenger vehicle, 1,500 kilograms, okay, it would take you a little over 5 meters to come to a complete stop under perfect road conditions, okay, from 30 kilometers an hour. Okay, 5 meters may not seem like that much. Guys, from here, it's a ways. Okay, you better hope you saw that kid pretty early. All right, now, realistically, how fast do most people go through a playground zone? 40. Yeah, everyone does that, right? It's just 10 kilometers an hour, right? Nobody thinks about it. It's just 10 kilometers an hour. Okay, well, you got to remember, speed is exponentially related to your energy, and thus it is exponentially related to your stopping distance. Okay, so let's say we're going 40 kilometers an hour. We'll just figure out what that is in meters per second. It's 11.1. So we'll do the same calculation that we just did with 11.1 in there. It's almost double. It's only 10 kilometers an hour, but it nearly doubles how long it will take you to stop. Okay? Speed's exponentially related to your stopping distance. Okay? That's not something they ask you on the driver's exam, but it's something they should, because it's something people don't understand. If people understood it, nobody would go 10 kilometers over the speed limit through a playground zone. Okay? Because, yeah, if that kid darts out in front of you 7 meters in front of your car, that 10 kilometers an hour makes a difference. Okay? Makes a difference between whether those parents have a kid that night or not. It's a big deal. Okay? I don't say that facetiously either. I say that as a parent. Go 30 in a playground zone. Okay? It makes a huge, huge difference. If you went double, if you went 60 through a playground zone, and I'm not saying you would, but there are idiots out there who do, 20 meters. Over 20 meters. Double your speed, 4 times the kinetic energy. 4 times the stopping distance. Okay? You go from being able to stop to running over and driving right on past another 15 meters. Okay, that's pretty bad. Agreed? Okay, keep that in mind when you start driving. Okay, it's the same thing, guys, in a construction zone. Why do you think speed fines double in a construction zone? Okay, if you're, and you see people do this, like especially on Deerfoot, right, where it's 50, and the sign is 10 kilometers before the construction, people get upset. I've been going 50 for 10 kilometers. I haven't seen any construction. I'm going to speed up. Okay, and they rip through that construction zone at 100 kilometers an hour. Okay, they've doubled their speed. They've quadrupled how long it would take them to stop. Okay, and at 100 kilometers an hour, you can do a lot of damage. Agreed? Okay? Just little things to keep in mind. There's physics behind all of that stuff. People don't just arbitrarily decide they want you to go slow. Okay? They're not doing it just to make you late. Okay? They're doing it because simple physics. All right. Hey, look at that. I did the same thing last semester. I do it every semester. I just forget sometimes. All right. So, which has more kinetic energy? Semi-truck going 30 kilometers an hour or a bicycle going 30 kilometers an hour? Okay, why? Has more mass. Mass still makes a difference. Okay, if you're driving a car and a semi-truck, and then the semi-truck could take twice or 3 times or 5 times the distance to stop, depending on its mass, even if it's going the same speed. Okay, that's something else you have to consider. If you drive a big truck, you can't stop as quickly as a small car. Right? Now, I mean, there's other factors involved. Small cars usually have smaller brakes. Bigger cars have bigger brakes, and that makes a difference in how quickly you can stop. Okay, but it comes down to mass. Okay, if you've ever watched, you didn't watch Highway Through Hell? It's on the Discovery Channel, the towing show. Okay, you can see that mass makes a huge difference because those semi-trucks just don't stop. Okay, they put their brakes on and they just keep sliding. Is that the collision avoidance, where the computer applies the brakes early? I haven't seen that. I've seen the one where Jean-Claude Van Damme straddles the two, that was pretty cool. Because they now have the autonomous driving essentially in those. So if the driver falls asleep, it's got sensors that can see the lines in the lanes, and it actually kind of autopilots and then stops. Because two drivers would have probably made Van Damme fall between, but the computers just drove the truck straight. So, yeah. All right. The other stuff has to do with thermal energy, which we haven't talked about yet. Okay, so here's what we're going to do. Okay, I want you guys to try this one. We're going to go over some examples, okay, of work energy theorem kind of problems that you might encounter. Okay, we might get through this first one. Okay, a rubber band is stretched 0.85 meters by a force of 60 newtons. Okay, at what speed would it propel a 0.125 kilogram ball when released? Okay, so here's what you have to think about when you read a question like that. First, I'll let you write it down. Then I'll tell you what you have to think about. Okay, so here's one of the things we got to think about. First off, work's a change in energy. Okay, if I pull back on a rubber band, I exert a force through a distance. Okay, so I can calculate how much work I do on this rubber band because I know the force I applied and the distance over which I applied it. Okay, now once I do that work, is there energy in the rubber band ball system? Yes, there is. Okay, if I release the rubber band, what will the rubber band do? I was actually thinking of one word. Work. Will it do work? It has energy stored in it, right? Energy is the capacity to do work. If I release the rubber band, it will exert a force through a distance on the ball. Okay? So will that change the kinetic energy of the ball? Yes, it will, because the ball will go faster. Okay? So essentially, what we're saying here is the same thing we said just a minute ago with the car's brakes. Okay? What we're saying is that work, okay, will change the kinetic energy of the ball. Okay, so it's going to change EK. What's the initial kinetic energy of the ball when it's sitting in the rubber band? 0. So I don't really need to put in that the initial energy was 0. I just need to figure out that the force multiplied by the distance equals the final kinetic energy of the ball. Because like we said, once I do work in a system, that work stays in the system. It just gets transferred around, okay, converted into other forms, but it's still there. So the work I do initially on the rubber band will eventually become the kinetic energy of the ball. So since I know the mass of the ball, I know force and distance, can I calculate VF? Yeah, I just have to manipulate. Okay, so how do I get VF by itself? What two things do I need to move? Andreas? Half an m, right. I want to leave VF by itself, right? So, you divide both sides by half of m. Okay, cancels over here. Comes over to this side. All right, now, I want VF, not VF squared. So what do I have to do? Square root. Okay, so very similar to what we did with the car, except for the car one I was solving for D. Now I'm solving for VF. Okay, doesn't really make a whole lot of difference. All right, so now I can plug in my numbers. Okay, so we'll have the square root of 60 newtons times 0.85 meters divided by 1/2 times the mass of the ball, which was 0.125. Okay, 28.6 meters per second. Perfect timing. Okay? All right. Have yourself a good weekend. Guys, remember your Need for Speed Labs are due next week, okay, on Tuesday. So you might want to take a little time on the weekend and get it done.